Today we're going to start talking about data structures, ways of organizing data within the computer to make it accomplish certain tasks more efficiently. To start, we're going to talk about two very fundamental abstract data types called stacks and queues. At first blush they seem quite simple, but actually they lie at the heart of many computational procedures. As with everything we do, we're going to precisely describe these abstractions with APIs. But first, just a little review of the distinction between data types and data structures. So we know, and we've talked from the beginning, a data type is a set of values and a set of operation on those values. Some of the data types are built into Java, like int or double or string, but most of the data types that we use are not built into Java. We define them ourselves, like complex or picture or charge and other examples that we have considered in this course. And we describe the data types with APIs, and these are just examples that we've considered in earlier parts of this course. So data structure is a different thing. That's about representing data within the computer and relationships among data. And you'll see in this lecture that even with a few very simple mechanisms, we can build quite intricate data structures. Sometimes data structures are built into Java. For example, arrays are an example of a data structure, one-dimensional or two-dimensional, that are built into Java, where we can store tables of numbers or any kind of object. But most are not, and that's what we're going to start looking at today. We're going to look at linked lists today, and next time we're going to look at trees. And they can take all different types of form. So for every data type, you have a set of values, you have your data, and there's a design challenge, which is what data structure should we use? There's two primary resources that come into play. The first one is how much memory is needed, and the second one is how much time do the data type methods use given that data structure. And those are going to inform the design decision every time we define a data type that is going to involve processing a significant amount of data. So now let's look at the APIs for stacks and queues. And they're examples of collections. Collections, an abstract data type whose values are a set of items that are all of the same type. We say a multiset because they could be equal. Several actually of the fundamental collection ADTs, in particular the stack and the queue, differ just in a detail of the specification of their operations. So let's look at a stack. The basic operations for a stack are to add a new item to the collection, and we say we add it at the beginning. And then the second operation is to remove and return the item most recently added. That's the specification of what that operation should do. That's called a LIFO discipline, last in, first out. So we take away from the beginning. Those are the stack operations. And then we also want to test if there's any items there, test if the collection is empty, and we want to know the size of the collection. So those are the basic operations that characterize a push-down stack. A queue is very similar. The only difference is the specification of which item to remove and return. For a queue, we think of adding new items at the end and taking items from the beginning. That's called a first in, first out discipline. And again, we test if the collection's empty, return the size of the collection. So those are very similar abstract data types. They only differ in this detail of the specification, whether we use a LIFO or a FIFO discipline to decide which item to remove and return. Now these two data types arise naturally in countless applications, and we'll examine a few of them in just a bit. One of the key characteristics that we want to emphasize is there's no predetermined limit on the size of the collection. From the point of view of the program, there's no limitation on how many items can go into the stack or how many items can go into the queue. And that's very important conceptually. It allows the design of code that can survive the test of time. As computers become bigger and bigger, the programs can operate with more and more data because there's no specification about the size of the collection. And we'll come back to that point in a minute. It's a subtle point, but it's a really important one that we want to emphasize in this lecture. All right, so let's look at some examples of a stack in operation. So we're talking about we name the operations push and pop. Push is add an item to the collection. Pop is remove and return the item that was most recently added. So if we push 2, then push B, then we put B at the top of the stack. Put another one OR, and you can see the items go to the top of the stack. So always we take the new item, put it on the top. Now we'll specify pop just by writing a minus sign. That says take the item most recently added to the collection, so we remove the 2 from the top in this case. And that's what we return, and then what's left in the stack is the other 4 in order that we gave them put them in from bottom to top. So that way we know that when we remove one, we take it from the top, right at the top. So now put B in, take the one from the top, that's B, then the next one is not. Now if we push that, that goes to the top, and so forth. So this trace of the operation example of stacks give you a good feeling of what this data structure is supposed to do. All right, by contrast, here's what happens with a queue with the same list of operations. So now we put the new items down at the end, and that's not in the specification, that's in the implementation of this example, but it allows us to remove and return the item least recently added. We take that one from the beginning or from the top. So DQ, again indicated by the minus sign, is remove and return the item least recently added. It's going to come from the top. Then we put another B on that goes at the end and remove the B and so forth. Again, remove from the beginning, add to the end. That implements the operation of remove and return the item least recently added. That's what happens with the queue. Okay, so that's the basic idea of those data types in operation. There's one other thing that we want is we want to be able to put any type of data on a stack or a queue. And that requires a little more effort in Java code. The way that Java deals with data structures like collections that are intended to work for any type of data is called generics or parameterized data types. And it's not that difficult to understand the code, and then if you look at our code and use it as a template, you'll be able to write code of this kind yourself. The idea is to, rather than using a real type name in the definition of the data type, we use a placeholder type name, actually within angular brackets. And then in client code, we put a real data type in for the placeholder, and let's look at how that works. We'll give some examples. For now, I just want to point forward to that kind of code so that we can specify the API. So rather than just say we want to define what a stack is, we want to say what a stack of items is. So inside the bracket is not a real type name, but a placeholder type name. We want to have a stack of items, and we want to be able to substitute any type of data for item. So the constructor creates a stack of items, and they all have to be the same type item. Then our push method takes an item as parameter, and again in client code that'll be substituted for string or integer or any other type of data. It doesn't return anything, just adds the item to the stack. The pop takes no argument, it just returns the item most recently pushed from the stack, and the type of that is our placeholder name item. Is empty returns a Boolean, says whether the stack is empty or not, and size is an int, which is the number of items on the stack. That's our specification of a stack. And queue specification actually is the same, except that the names are different. We call the add item to a queue method enqueue, and we call the remove and return the least recently enqueued item dequeue. And again, otherwise, the definition of the API is exactly the same, differs only in name. And then we have is empty and size. So those are our APIs, and we're going to look at some client code in just a second, and then we'll look at implementations. That's our specification of what these data types are. Now, but we're going to add one other thing because it's extremely important in many applications. And we've seen it already in several examples. Performance matters. And what we want to do is provide guarantees on performance so that not only is our client code simple, safe, and clear, but also efficient. We don't want to have performance bugs hidden within our implementations. And somehow we want to specify, when we're talking about what a data structure is, that it's got some performance guarantees with it. This is a little bit outside what you normally see in language specifications of libraries, but it's very important, particularly for fundamental data types like this. And we'll come back to this point often later on. So for stacks and queues, we want to have the specifications that, first of all the operations should take constant time. These are simple operations, should only take a few instructions. Shouldn't waste memory. If the collection's got a few items, we should only use a little bit of memory. If it has a lot of items, we should use a lot of memory, but linear in the size of the collection. Should only use a constant factor times the number for every item in the collection. If it's non-empty, of course, if it's empty, the size is 0. But if there's any number of items, the memory use should be bounded by constant times the number of items. And then the other thing I already mentioned is there shouldn't be any limits within the code on the size of the collection. As we'll see, it's kind of easy to solve this problem if you have such limits, but it's a much better design goal to say that our code can be used even way in the future when collections may turn out to be much bigger. We don't want to have to change our code to adapt to changes in technology. These are requirements, again, if the client code is going to be scalable, it's going to be useful in the face of Moore's law. Now, as I mentioned, it's typical in programming languages to say that if you implement the API, we specified the methods that we're going to use, then you have implemented the stack and queue abstraction. But we're holding our implementations to a stronger standard. We're going to say if you don't meet those performance specs, then you do not implement the abstractions. It's not a stack if some operation takes linear time or if the memory use is huge. It's not a queue if some operation takes more than constant time. Those are some other kind of data structures, but they're not stacks and queues. We're saying if you want to use that name, you better not only match the API, but also meet the performance specifications. Otherwise, you're talking about some other kind of data structure. As usual, before talking about implementations, let's talk about some client code so you can appreciate the utility of these data types. There's a huge number of applications. A queue is first come, first served resource allocation. So this is a line of cars waiting to get onto a bridge. Data transfer, standard in and standard out are examples that use the queue abstraction. First thing that you read in, you want those to come in the order that they were presented. Or if there's a shared resource within your computer system, any kind of shared resource, even in the real world, like this line, you want first come, first served. That's what queues do. And in all kinds of simulations of the real world, you want to be able to develop this discipline, and that's what our queue data type does. Stacks is a different kind of discipline. It's also real world. When you have a stack of books and you get another book, you put it on the top of the stack. And then maybe you're going to read the one on the top of the stack. It's maybe not what you wanted to do, but that's what happens in the real world. Last come, first served resource allocation. They actually play a critical role in programming languages. When we have function calls, and we did examples of recursive calls, those are implicitly stacks. The place that you go back to is the place that you most recently came from. It's a very basic mechanism in programming languages and computer systems, a very fundamental abstraction in computing. And we'll come to examples of that very soon. Okay, so here's a Q client example for standard input. Standard input now actually implements this. This is the read all strings. When we initially implemented standard in, we didn't have it, but we realized it's a fine example of a Q client. So we want to take all the strings that are on standard in and just put them in an array. And so that's the implementation that we're going to look at next. And here's a client, so we just want to read all the strings, put them in an array, and then print them out. Now this is get Moby Dick into an array, and then we can process that as an array of words individually. So the challenge in this is that you can't store the strings in an array before you create the array in Java. So when I'm implementing read all strings, I'd like to put them in an array, but I can't create the array because I don't know how many strings. And you have to know the number of strings in order to create an array in Java. You have to know how big an array you want to create. But you can't know how many strings there are in the input stream until you read them all. Now, you can various ways to get around this, but conceptually, that's the challenge that we're talking about. And it's easy to solve with a queue of strings. So let's look at how that works. So we're going to create a queue of strings, and now this is what client code looks like for generic data types. Our API said that you're supposed to put a real type name instead of the place of the word item inside the angular brackets. So in this case, we use string. So that's precisely how you say queue of strings. In the variable name queue, we create a new queue of strings. So that calls the queue constructor and also specifies that the type name that's going to be substituted for item in all the code is string. So now we want to, while standard in is not empty, we're going to call the enqueue method. So that says add a new item to the queue. And the type of that item is string. It's a queue of strings. And we're going to get that string from standard in, read the next string. So that, because the size of the queue is not specified anywhere, that'll work fine no matter how many strings there are in standard input. Then we get the size of the string because they're all there, they're all on the queue. Now we know we can pick out the value n, which is the size of the queue, and we can now create an array of that size. So that's an array words of size n. And then we can go through and take all the strings off the queue in the order that they came and put them in the array, copy them back into the array, and then return that array. So that's a fine example of client code that uses a queue to accomplish a useful task, putting all the strings on standard in into an array. In that code, if I have a machine in the future that has got 100 times more memory and I can read 100 times more strings, I can use that exact precise same code without changing it at all. That's the importance of this kind of abstraction. Stack example, we'll give plenty of examples later on, but just in the use of it in your real life, a typical scenario when you're browsing the web is you visit a page, click a link to another page, click a link to another page. All the system is doing is saving the links that you've been to on a stack, as shown in the bottom right in this slide. So when you click the back button, it just pops the stack and gets you to the most recently visited page. So even when you're using a browser, you're using a stack. Now there's one other point about parameterized ADTs, a technical point that I have to cover, and that's the idea of wrapper types. So the thing is, the generic type can't be a primitive type. Just the way the implementation of generics is built. So instead, the idea is that for many reasons, each primitive type in Java has a wrapper type that contains is kind of equivalent. It's got the same value, but it's got more capabilities. So for example, int is a primitive type in Java for holding integers, but there's a wrapper type for integer values that also can hold integers, but also has associated methods like parsing and other things that we've used. And it's a little bit technical, but it's useful, and we've already seen it in code. And in this particular situation, so first of all, one reason for the wrapper types is that they have large set of operations associated with a primitive type. But that's not what we're talking about now. The main thing now is that instances of wrapper types are objects, and then they can be used in any way objects can be used, like for example to invoke methods, but also as generic types. So we can say if we want a stack of integers, the generic type has to be an object, so we'll use the associated wrapper type. And then the other thing that makes this convenient in client code is that Java automatically does casts from primitive types to wrapper types when warranted. So when you say stack.push 17, 17 is an int literal, but Java knows that it needs to be an integer, object, so it automatically does that conversion at cast. We don't have to do it in client code. And similarly the other way. When we return a value from a stack that's supposed to be integer objects, and we assign it to an int, it's clear that the cast has to be done from the wrapper type down to the primitive type, and Java will automatically do that. You might not even notice this when you're writing code of this type, but anyway, it's important to mention that this is a Java language feature when we use primitive types for parameterized values in collections like stacks and queues. It makes the client code very simple without any casts, and we like client code with no casts. So now let's look at an interesting client example for stacks. This is called expression evaluation using a particular type of expression called a postfix expression. The way that you're used to writing arithmetic expressions, we use parentheses to express which operators, the order of performance of operators. Then sometimes there's rules that can help us avoid putting the parentheses, but generally, if you want to be sure, use parentheses to specify the order of operation. So this says you want to do the 2 plus 3 and the 4 times 5 before you do anything else. So you do those, and then that gives you an expression with fewer parentheses. Now we do the 5 times 20 and add that to 1, and we get 101. That's an infix arithmetic expression. There's another method for writing an arithmetic expression called postfix. And the idea is simply, if you've got two operands and an operator, you write the operator after the operands instead of in between them. And what's remarkable about postfix, you can see right away, there's no parentheses. And so how's that? You have to just take a look at the expression. Well, what you can do is go through to the first operator. Since it's the first operator, everything before it is operands. In particular, the two things right before it must be operands, its operands, so you can just evaluate, in this case 2 plus 3. Then go to find the next operator. And again, it's the next operator, its two operands have to be right before it. And similarly, you can go through and convert the postfix expression to an infix expression in this way. Don't need the parentheses. And actually what we'll see is you can just go ahead and evaluate these without even using the expressions if you have a stack. This is also sometimes called reverse Polish notation because it's invented by a Polish mathematician in the 19th century, 20th century. It's called reverse Polish because you could do the same thing. You put the operator before the operands and get the reverse. So this little proof here, this little example, you could extend to a proof to show there's only one way to parenthesize a postfix expression, and therefore only one way to evaluate it. Now, what we're going to show is that with a stack, we can do that evaluation very easily. By the way, postfix has a famous history. In the early 1970s, it was used as the basis for the first handheld calculator because it was deemed a little bit too confusing to deal with parentheses when doing calculations. And in fact, that calculator, when you said enter, that really means push onto the stack. And people got very used to making calculations basically using postfix with some mental model of the stack. Just take the two things I most recently computed and compute with them. That's one of the first handheld calculators in the 70s. No parentheses involved, and actually that calculator turned out to make slide rules obsolete. Slide rule is a decidedly non-digital computational device that people use for many years. If you don't know what they are, you might be interested in reading up about it. Okay, so let's take a look at postfix arithmetic expression evaluation using a stack. It's a very simple method. If you have something left on the input, read it. If it's a value, just push it on the stack. If it's an operator, then take the last two values from the stack, apply the operator, and push the result back. Let's look at how it works for this example. 1's a value, so we put it on the stack. 2's a value, we put it on the stack. 3's a value, we put it on the stack. Now we come to plus, which is an operator, so we pop the two things, 2 and 3, perform the operation, and push the result onto the stack. Now we encounter 4, put that on the stack. We encounter another 5, put that on the stack. Now the next thing is the times. We pop the two top things on the stack, perform the operation, put the result on the stack. Next thing is another operator, pop the two things from the stack, perform the operation. Now we get 100, put the result on the stack. And then the last thing is another operator, pop the two operands, perform the operation, put the result on the stack. If there's only one thing on the stack and we're at the end of the expression, that's the result. Very easy method for evaluating arithmetic expressions. And here's what the code looks like. So we have a stack of double values. As long as standard in is not empty, we're going to read the next string on the standard input, which might be a number or an operand. If it's a star, what are we going to do? We're going to pop the top element on the stack and multiply it by the next element, which we also get by popping. Take that result and push it on the stack. Same for plus or minus. So there's a minus stack.pop there. Or divide. All of those kinds of operations are extremely straightforward. We could even do something like square root. For a token square root, that only takes one argument, so we just take the square root of that and pop it. And you can develop this to include whatever operations that you might want to write down. And then if it's none of those things, we'll say, okay, it must be a double value. We're not checking for errors here. And so you just push that token is a string that we want to interpret as a double value. So we use double.parse double to get it to be a double value, and we push that. That's it. That's the entire postfix evaluation. Then when we're done, when we've read all the tokens from the input, we take the top thing from the stack, and that's our result. And so that program, that little 20-line program, does expression evaluation. It produces 101 for our example. Or if you say something like 1, 5, square root plus 2 slash, that's equivalent to 1 plus square root of 5 over square root of 2, and that's a golden ratio. Extremely useful piece of code, and if you want to implement other operations, you can go ahead and do it. It's a very natural paradigm for computing. So very easy to add any operators you want. It's actually, in the book, we have an example where you can actually just do infix if you don't like postfix with parentheses and all. And that requires 2 stacks, one for operators, one for operands. It's only slightly more complicated than this one, and a very fundamental and famous algorithm. We don't have to actually perform the operations. We could actually modify this to write the machine language code that performs the operations. It takes a little thought to understand what's going on there, but it's not that difficult. You can take the expression and turn it into a program that evaluates the expression. And actually, that's an indication of how the Java compiler works. Very much similar to this. If you've got an if for a while, you've got more to do, or you've got more different kind of code to put out, but still the idea of using a stack to keep track of parenthesizations, or in the case of Java code, you have to keep track of nested braces and other things like that. Still, stacks are the basis for how the Java compiler is able to figure out what your program's supposed to do and to put out machine code that does it. And we'll come back to that in just a second. Here's another example of stacks in the real world. This is the PostScript language developed by Warnock and Geschke in the 80s. And their idea is to create a turtle with a stack as an effective way to write programs that can produce graphic output, graphic image, even images using text. So PostScript program code is, if you have a literal value, it's implicitly pushed on the stack, just like a postfix expression. And anything else pops its arguments from the stack, performs whatever operation it's supposed to do, and puts the result back on the stack. Sometimes you can add commands that drive a virtual graphics machine, like a turtle machine. And you can also add loops and conditionals and everything else that a programming language like Java has. Again, it's the marriage of graphics, turtle graphics, with a stack to get a very expressive programming language. So here's an example of some PostScript code. 100, 100 move to means push 100, push another 100, call move to. That's the turtle command, and where's it supposed to move to? XY coordinates. Where's it get the XY coordinates? From the stack. Pop Y, pop X, and move there. 100, 300 line to. Again, that's 100 puts 100 on the stack, 300 puts 300 on the stack. Those are XY coordinates. Line to is a turtle command to draw a line to that place. What place? Pop Y, pop X, draw a line there. 300, 300, line 2, 300, 100, line 2. Those define a path that the turtle has traversed. And then the command called stroke is a graphics command that applies a stroke to that whole path, actually drawing it. So that's a PostScript code for drawing a square. Actually, if you, in a lot of computing environments nowadays, if you put a %, exclamation point in front of that code, and double click on the file, you'll get a square if you're lucky, or maybe it takes a little more work. This is a very simple virtual machine, but it's definitely not a toy. The way that Warnock and Geschke used this was to develop applications where it's easy to specify what's in the published page, easy to implement on lots of different printers, so that's because it's got this simple turtle graphics model. And this ushered in desktop publishing, completely revolutionized the world of publishing. And nowadays, everything, packaging, books, magazine, papers, even quite a bit of web content is specified. The image that you see is specified in terms of PostScript code, which is built on a stack. Another important example of a stack machine is the Java virtual machine. When the Java compiler converts your code into simpler code for execution by machine, it's actually using a stack machine. And there are programming languages and other machines out there that are based on stacks. And again, the whole concept of a stack, the operation should be constant time, and the stack can grow without bound. There's no limitations within the program on the size of the stack. Means that something like PostScript, which was developed over 30 years ago, is still in use today because there's no restrictions on the size of the stack within the code. And it's an extremely simple model that's able to be implemented on all sorts of machines. So those are some examples of client code. Now let's look at implementations. We'll start with the Strawman implementation that's extremely simple and was actually used often in the early days of computing because it's so simple, but it points out the challenge of actually implementing the API that we've set down. So this is a warm-up. It's called a Strawman. We're going to simplify the specification a little bit. First of all, we're only going to implement it for one type of item, say strings. And the other thing we're going to do is to have the client provide a stack capacity in the constructor. And the rationale for doing this is that we can just use an array of strings to represent the values. So let's take a look at now the API that we're changing a little bit. So first of all, in the constructor, we're specifying the capacity of the stack. And then when we push, we'll push a string, and we pop a string. This is just to get started to look at how simple the code can be in a specific situation like this. So it's a little different API than the one that we specify, but it'll get us looking at implementation code right away. And the whole idea is that with this we can represent the collection with an array of strings, and once we have that decision that we're going to use that data structure, an array, then implementation of these methods becomes extremely simple. So what we're going to do is keep the items in the stack in order in the array, and then n is going to be the index of the next open position in the array, and that's also the size of the stack. So it's a kind of an upside down representation of the stack. The top of the stack is like later on in the array. But if you do this, then we start with what's our data type. Our values are an array, and then an int, which is the size of the array. And then our constructor is just create a new, if the client gives us a capacity, we create a new array of that size. Those are the first two parts that we need to do to implement the data type. The instance variables are an array and the size n, and then the constructor just creates that array. And then given that, now to implement the operations, well, let's do the test client first. And this is a test client that is that performs like the examples that I showed right at the beginning. What we're going to do is read strings off standard input. While it's not empty, we're going to take an item. If the item is a minus sign, then we pop and print the result of popping, just like we did in our examples. Otherwise, we push, and that's the test client. So that's the example we gave at the beginning, to be or not to, pop be, pop that, pop is, gives that result. Just as the example that we went through. So that's a test client. You can see the constructor provides a maximum size that's taken from the command line in this case. So if we ran this with max too small, then there'd be an error. And that indicates the kind of problem you have when you start talking about capacity, or even with a simple test client. So that's what we expect the thing to do. Even it's worthwhile, before going further, just to think about an amusing question. So this is the way our test client works. So if we do 655 4, 3, 2, 1, pop, 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 it comes out 1, 2, 3, 4, 5, 6. Or if we do 1, pop, 2, pop, 3, pop, 4, pop, 5, pop, 6, comes out in order. Or this more complicated, 4, 1, pop, brings out the 1, 3, 2, pop, 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 brings out 2, 3, 4, 5, 6, pop, pop, brings out 5, 6. Comes out in sorted order. That's an interesting question. Can you always put the pops so that you can get them to come out in sorted order? The answer to that question is no. For example, if you have 5, 6, 1, there's no way that the 5 can be popped before the 6 and after the 1. Mathematicians study how many different ways are there to create strings like this where the atoms come out in sorted order and so forth. Even such a simple data structure can lead to fascinating mathematical questions. On a queue, this is a boring question because they always come out in the order they came in. So if they're in sorted order, it doesn't matter where the DQs are. So to complete our implementation, we have to do the methods, the data type operations. And with this data structure and the restrictions that we made, these are extremely simple. They're one-liners. So what's is empty? That's just is n0. What about push? Well, all we do is we take our new item, we put it in A of n, and then increment n. And that's accomplished with one line of code in Java. After the push, the new items there, and n has been incremented by 1. And for pop, we do the reverse. We decrement n and then return the item that's in that position. And then what's the size is just n. They're all one-liners. Extremely simple to implement. And that's a full implementation of that Strawman API that we gave. Constant time one-liners, and even in the simplest kind of machine language, these things are going to be only a few instructions. And so the very first computer systems that needed to use stacks to do things like evaluate arithmetic expressions and function calls would use implementations like this. That's the complete implementation, the instance variables, the constructor, the methods, and the test client. And it produces the desired result. So now, here's a trace of what happens. So this is in an array of size 20. And it's following the example that we gave, but the stack is upside down. So a very simple computation, really. But the thing to notice about this simulation, you can see immediately why capacity is kind of a situation. There's a lot of space when the stack size is not near the capacity. And that's actually typical. A lot of times when you're processing data, you have to reserve for the worst case, the biggest capacity. But most of the time you're operating at way under capacity. And in a typical computing application, you might have a large number of stacks and all that wasted space. That's the reason that we want to have that performance requirement that the space should be linear in the number of elements actually in the stack. So let's do a quick benchmark. What this thing implements, the Strawman stack, is not really a stack. It's a fixed capacity collection that behaves like a stack if the data fits. And that's a lot of restrictions. It does not implement the stack API, number one, because it requires the client to give capacity. And number two, it doesn't meet the performance specs. So the API says it shouldn't be an argument to the constructor, but StrawStack requires a capacity. It only works for strings, so it doesn't do the generic thing, so that's okay. We know how to do that. It does get all operations done in constant time, but it does not meet the requirement that memory use should be linear in the size of the collection. And there are limits within the code on the collection size. That's the use of max there. So StrawStack is not a stack. It does not meet the performance specs. And so we're going to have to look at some other way to meet the performance specs. And what we need is a new data structure, and that's what we're going to talk about next. The new data structure that we're going to use to implement stacks and queues is called a linked list. It's a fundamental data structure with all kinds of applications, and that's the one that's going to solve this problem for us. So the idea is a distinction between sequential and linked allocation of memory to hold data. Sequential data structure, or an array, we put all the objects right next to one another. In your computer's memory, they just go consecutively in the memory of the computer. Here, this is pointing ahead a little to a small machine that we're going to talk about in detail later in the course. The memories have names, and here the names all begin with C. And the items are stored one after another consecutively in the memory. It's like a Java array. The thing is fixed size, but you can get quickly to any item in there. That's a sequential data structure. A linked data structure is a different thing. There, we're going to associate with each object a link to a different object. In this case, what we have in the computer is a memory address of another object. So over on the left is the names of the objects, where the objects are located in the memory. Every object has associated with it the name of another object in memory. So in this case, Alice is linked through the memory address to Bob, and Bob is linked through the memory address to Carol. And Carol's link is null, so that indicates the end. In Java, these things are called references. That's the Java name for the memory address. And we're going to work with Java code, and then later on we're going to talk more detail about how things are represented in a machine. So the whole idea is that the size of the structure is variable. It's just as many links as you have. They're not stored next to one another in memory. And the only thing you can do is get to the next element in the memory, the next element in the sequence each time. Most novice programmers don't get this far. This is a level of sophistication that's not reached by a lot of programmers. It's not very difficult, but it's quite different than the idea of using an array to access a place in memory. And it's an introduction to a whole new world of organizing data, and we're going to see another more important example in the next lecture. It's very flexible, and it's very widely used within the system, and it's important to understand the concept of linked data structures when it comes to efficiently processing data and implementing algorithms. So the very simplest linked data structure is called a linked list. And there's one way to think of it is as a recursive data structure. A linked list is either null or a reference to a node, and a node is a data type that has a reference to a node. So if we unwind that recursion, we can say a linked list is a sequence of nodes, or it's a node followed by a linked list. There's a number of ways to unwind that recursion. And so what we do to represent a linked list is use a private class node to implement the node abstraction. At first this is a little complicated, but it's actually very simple. And we use this one construct to create all different types of data structures. So taking the time to understand it in this simple context is worthwhile. So we're going to start with nodes just having two values, a string and a node, and we can add generics to the code and so forth later. But let's just work with a node is a data type that has a string with it, and then it's got another value which is a reference to another node. And that's what that data type is. So we're going to use this as a nested class within our code so we can refer directly to these variables item and next within any given node. So it's a string and a reference to another node. And so this diagram shows an abstraction of a linked list built from nodes. The first is a variable that's a reference to a node. That node its item is got the string Alice, and its next is a reference to another node which contains Bob and so forth. That's a linked list. It's an example of a linked list, and we're going to use Java code like that to build linked lists. Now, even with just one link like this, a value and a link to another node, things can get pretty complicated. We talked about this simple one, but you could have multiple nodes pointing to a given node. That creates a structure called a tree. Or it could be circular, or you could get a row shape, or in general, you can get a pretty complicated mathematical shape. This just indicates how powerful this abstraction is. We're going to stick for now just with the simplest, the linked list. Actually, next time, so the thing is, from the point of view of any particular object, the data structure could be any one of these things. We have to ensure in our code that we have the simple one. Next time we're going to talk about structures that have more than one link, and then there's lots more possibilities. It's a very powerful concept, the idea of structuring data with links. So let's look at what Java code that creates a linked list might look like. And again, we've got a abstract representation of what the memory of the computer might be like over on the right. So we've got a variable third that's of type node, so that's going to be a reference to a node. We say that's a new node, then Java's going to allocate 2 spaces for it. One actually be a reference to a string, but in the example we'll just put the string in, and the other will be a reference to a node. So if we say third.item equals Carol, we can refer directly to item, given the variable, because we're using an inner class. Third.next equals null. Again, it would be a reference to the string Carol and be more complicated, but let's think of it in this way. That's what we're going to get. There's a node with a variable that's a reference to a node. That node contains a string and another reference. In this case, it's null. Or in our diagrammatic representation, that's what we've got so far. So now let's create another new node. Now the system decides where it's going to be in memory and just returns a reference. And yeah, C9, CA, CB, you'll understand what that means in a couple of lectures. Second.item equals Bob, and second.next equals third. So this is linking the node containing Bob in front of the node containing Carol in the list. So now we have second points to Bob, which then refers to Carol. And how do we get that link to Carol in there? That last line, second.next equals third. Third's a reference to the node containing Carol. Second.next is a reference to the node following Bob, and that simple code gets that done. And again, if we want to put another one in, first equals another new node, that's Alice, and then we say first.next equals second, that links Alice in front of Bob. That's an example of code for building a linked list. We're not going to write a lot of code like this, but we're going to write some code like this, and the point is that with the ability to manipulate links and references, we can build rather complicated data structures. Before higher level languages like Java, when people were writing in much lower level languages, building lists was done with lower level code, and there's a lot of standard operations developed for processing data that's structured as a singly linked list. So like one thing you might want to do is add a new node at the beginning, or remove and return the node at the beginning, or add a node at the end. Well, actually you need a reference to the last node in order to be able to add a new node at the end, so you can't always do it. Or traverse the list, visit every node in sequence. For many years, we would teach in introductory programming courses quite a bit about writing code of this type. Sometimes we might have a doubly linked list, which we're not going to do. It's where each node points to the one after it and the one before it in the list. In that one, you can maybe remove and return the node at the end and other types of operations. So let's look at what these first couple of basic operations look like with just a singly linked list. How about remove and return the first item in a linked list? Well, we can get the item, the string, by just first.item, and we'll put that in a variable. And so now we have that first item stored away. So now how do we remove it from the list? Well, it's actually very easy. Just say first equals first.next. And that will, the first, refer to the same place that Alice's next field was referring to, and that's Bob. And what's really significant about this is it leaves no reference to Alice. In Java, that's no problem. That's precisely what Java's garbage collection system is for. Eventually, Java will find that memory and reclaim it for later use. And then we just return item. So 3 lines of code, we can remove and return the first item in a linked list. Very simple code. And what we're left is with the list that just has the later 2 items. What about adding an item to the beginning of a linked list? Well, it's just manipulating the few pieces of data that references that we have available. So we're going to say that after we're done with this, the Alice is going to be the second node in the list. So we save that away. Second equals first. And to put Dave in, we're going to need a new node. So first equals a new node. And so now we've got first as a new node, and then we got the rest of the list pointed to by second. So we fill in the new node. First.item equals item, that puts Dave in, and first.next equals second. Now we've got a linked list, and the second variable is no longer relevant. But it's critical that we held on to that before we reset first to be new node. If we hadn't done that, there'd be no way to access anything in the list. That's the kind of challenge that we face in developing list processing code. What about traversing a list, visiting every node on a list? Well, that's just a simple while loop, or you could do it in a for loop as well. X equals first, while X is not null, print x.item and set X to x.next. So print x.item, that's Alice, set X to x.next. Just moves right through the list. It's not null. Print out the list in order. So that's 3 examples of operations on linked lists that are easy to code. So let's look at a couple of pop quizzes, and I'll not address these directly. I'll leave these for you to study and look at the answers. So here's a more complicated piece of code that processes a list. It reads from standard in, and it does a few operations on the list and then goes through it. The answer is, what it does is it winds up printing the strings from standard in on standard out, but in reverse order. So it reads them in and then puts them at the beginning of the list, which winds up reversing them. Better to use a stack than this, although this code is kind of implicitly within the stack implementation that we're going to look about. So here's the code that uses a stack to do it. One reason we don't teach that much list processing nowadays is that most of this kind of processing is embodied in higher level data structures like stacks. Here's another one, and again, this is worth a little bit of study just to cement your understanding of linked lists. This one, it turns out, puts the strings from standard in on a linked list in the proper order. And it does that by adding nodes at the end of the list by keeping track of the last one in the list. Again, this kind of processing is embodied in our queue implementation, as we'll see in a bit. So those are basic examples of code that process linked lists. Next, we're going to look at how to use code like this within an ADT implementation to actually implement the Stack API. So with linked lists, a rather powerful data structure, we can actually develop an implementation of the push-down stack that actually implements our API and meets our performance requirements. So again, push-down stack's an idealized model of a lifehouse storage mechanism. We have an ADT that allows us to write useful Java programs that manipulate stacks, and that's our API. But we also have performance specifications. The operations have to be constant time, the memory use has to be linear in the size of the collection, and there have to be no limits within the code on the collection size. And if implementation doesn't meet these specs, we say it implements some other kind of data structure, but not a push-down stack. So let's take a look at how we're going to implement it using a linked list. So that's our choice. We're going to hold the collection in a linked list. So the objects in the stack are going to be nodes in a linked list, and we're going to have just a single variable first that points to the node within the linked list. So what are the instance variables in the constructor that are going to support this use? We're going to have a variable first, which is the first thing on the linked list, and that's going to get initialized to null. And we're going to keep track of the size of the stack in an int variable n. And we need the private class node, and we can use generics within that class that allow us to develop this code to hold, for a stack to hold any type of data. And then every node has a next field that has a reference to another node. So that's the code that we need for instance variables in constructor. Our instance variables are reference to the first node and the size of the stack. Now, there's something that doesn't quite work. That's not really a problem here, but it'll come up later, or it might come up if you try to imitate this code in other contexts. You can't declare an array of generics. So you need to cast. If you need an array of items for some other more complicated thing, you have to cast it from an array of objects. And I'll just list that for later reference. Okay, test client. Our test client is the same, except now we can use the generic stack, which we didn't do for the Strawman thing that we had before. So that's the test client, and so we expect it to work no matter what type of data that we put in. We could have a test client with integers or whatever else, and our implementation would work as well. So that's what we expect out of the implementation. So now all that's left is the methods. So how are we going to implement the various operations? So first one is empty. One thing we could do is just say is first null. If there's no nodes in the linked list, then the stack's empty. Since we have n, we could also test if n equals 0 as well, and that's equivalent. Okay, how do we push a new item onto the stack? What we're going to do is put a new node at the beginning of the list. And we looked at that code. So that's second gets first. First gets a new node. First.item gets the item that we're supposed to put on the top of the stack. First.next gets second. That's exactly the code that we looked at for adding a new node to the beginning of a list. And then we increment n because we have a new item on the stack. So that's the implementation of push. And remember, first is our instance variable. Pop. So what do we want to do for pop? The most recently added item to the stack is the first item on the list. So what we want to do is remove and return the first item on the list. So in that case, we pull off first.item. That's, again, this is the code that we looked at for list processing. Say first equals first.next, and that makes first skip that first node and releases it for garbage collection. And then, since we removed an element from the stack, we decrement n, and then return the item. That's the implementation of pop. And then size is just return n as before. So it's a bit more complicated than the one-liners that we saw with the array representation, but the significant difference is that this implementation is going to meet our performance specifications. So that's the summary. There's the instance variables. There's the nested class for node. Those are the methods, and the test client we already looked at. And it's got the behavior we expect. Here's a trace showing the new items going on to the front of the linked list and then being removed from the front of the linked list. I pop from the beginning and push to the beginning of the list. And just looking at this diagram, you can see that the space used is just a multiple of the number of items in the stack always. If the thing grows to be 1,000,000, there'll be 1,000,000 nodes there, but when it's 3, there's only 3 nodes there, and that's meeting the performance specification in terms of space. So that's a trace. So now let's benchmark this against our specifications. So it completely implements the API that we gave, and all operations are constant time. There were just a couple of statements to add an item to the beginning or remove an item from the beginning. The memory use is linear in the size of the collection, and there's no limits within the code on the collection size. Again, at the beginning of this lecture, you may have thought that this is a relatively simple problem. What's all the bother? But when you think about it, this is actually a profound step in being able to meet performance specifications of this sort. And as you saw, the ability to do so is extremely important in real-world applications like the Java virtual machine or PostScript. And it's all made possible by introducing the concept of a linked data structure. It's also possible to implement the queue abstraction with a singly linked list, and you can see that in the book. Its DQ is the same, but NQ is a little more complicated, and you can see that in the book. So in summary, we've got these two basic data structures that are fundamental abstractions. They only differ in the order in which items are removed. And they have these performance specifications that really characterize them. You'll find implementations that claim to be stacks and queued that don't meet these performance specs, and they're generally not really acceptable for industrial strength applications. And what this points out for us is that linked structures are really a fundamental alternative to arrays that allow us to do things that we can't do just with arrays. And in particular, we've shown in this lecture, they enable implementations of the stack and queue abstractions that we couldn't meet just with arrays. Next, we're going to talk about symbol tables, which is a more difficult problem that uses doubly linked structures, again, to meet performance specifications and that support a huge range of important applications.